Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about numerical methods in mechanics using computers to help us predict how things are going to move over time. So why are computer methods useful? Well, they're not always necessary. Here's a famous historical case here of Galileo standing on top of what was not yet leaning Tower of Pisa and dropping objects. And it was there exists what's called an analytical solution to this problem. You can write down an equation for when you drop an object. If it's a heavy object and it's going to undergo a constant downward acceleration, you can predict very accurately how the object is going to move over time. So Galileo was able to write down that the y coordinate of his object was equal to its initial position minus 1/2 gt squared. And that formula is just a specific case of a more general formula, which says that if an object is undergoing constant acceleration, you can write its position as a function of time in the following way. So this formula that we just wrote down assumes that the acceleration is constant. It's only valid in cases in which the acceleration is constant. And we would call this an analytic solution. An analytic solution, that's just a fancy way of saying that we can write down a formula like this one, where we can just, if we want to know where the particle is at any given time, we just plug into the formula, and the formula tells us where to find it. So we would call this an equation of motion, and that is just you plug in a value of t, and at any given time t, you can find out where the object is located. So Galileo realized that as long as the objects being dropped were heavy enough, and you could neglect the effect of air resistance, the object would undergo a constant acceleration of minus 9.8 meters per second squared. And when objects undergo constant acceleration, it's very easy to write down an analytical solution for the problem. So you can predict where the object is going to be at some later time once you know what its initial conditions are, what its initial position and its initial velocity. If you know the constant acceleration, you can predict where the object is going to be later on. And if you read a textbook like the Wolfson textbook, these situations in which there's a constant acceleration are given a lot of attention. And I would argue it's in part because of the fact that those are cases where you can write down these analytical solutions. So it's easy to write textbook problems because you have analytical solutions that you can write down. You can write lots of textbook problems. But unfortunately, the real world, acceleration being constant is often not such a great approximation. So if Galileo had dropped a ping pong ball from the Tower of Pisa, uh, as you probably know, the acceleration of a ping pong ball, where the air resistance forces become significant, the acceleration is not constant. The acceleration depends on how fast the ping pong ball is moving, and therefore it changes over time. And it's very difficult to write down an analytical solution for the case where the acceleration is not constant. And that's where computers come in. These numerical methods using computers can often make life a lot easier if your goal is to predict the motion of objects for cases where the acceleration is not constant. So let's see how that works. And the numerical method that we'll use is a method known as Euler's method, after the great Swiss 18th century mathematician Leonhard Euler. And Euler's method, let's say a few things about it. One is it works for both cases of constant and non-constant acceleration. So it works for both constant and non-constant acceleration, like so. But it does assume some knowledge of what the acceleration is. So it assumes some knowledge of the acceleration. So we'll start off with the case of constant acceleration. We'll explain how Euler's method works in the case of constant acceleration, a case where you know what the acceleration is, and let's see how that works. So let's assume a situation is similar to the one described where Galileo was dropping balls off the Tower of Pisa, where you have a situation where you know the acceleration, we'll call it A, to be a little bit more general, and you know the initial conditions. You know where the object is at time zero and what its velocity is at time zero. And let's suppose the actual motion of y as a function of time is given by this blue curve. So maybe Galileo tossed the ball up in the air a little bit, and it's following y is initially increasing, but then it starts decreasing. And the idea in Euler's method is that you break up time into short chunks of time, delta t. So delta t is this time interval here, and you're breaking up the world into short intervals of time, delta t. So when you go to time 1, the velocity is going to have changed. The velocity at time 1 is going to be the initial velocity plus a times delta t. And we're going to say that we've updated the velocity. And now the position, the updated position, y1, we're going to write as the initial position plus this new velocity, v1, times delta t. And we're going to say that this formula, this line here, updates the position. Now, you can quibble and you could say, why did we use v1 here? The velocity was changing during the interval of time delta t. It started off at v0 and it ended up at v1. Might have been better to use the average of v0 and v1 here. That's a quibble. For now, we're just going to write it as v1. That's simpler, and it turns out that you do okay just by making that simpler assumption. And then the other thing we'll say is that this is clearly not an exact relationship. I really should put wiggly signs here. And you see that in the graph here. The position of y1 does not give you the exact value of where the object is going to be at time 1. It's just an approximate relationship. But the key point is that as you make this time interval delta t smaller and smaller, you can sort of see that if we had made delta t over here, then the error that we would have made would have been smaller. So this method is going to get, although it's approximate, the approximation is going to get better and better as delta t gets smaller. So approximation improves as delta t gets smaller and smaller. And now we just want to sort of iterate, to repeat what we've done. So if you want to figure out what y2 is, you can use the same method to get from y1 to y2. So what do I mean by that? So we're going to write the velocity is at time 2 is going to change. It's going to be whatever the velocity was at time 1 plus a, plus a times delta t. And now we can use this new velocity to calculate y2. And again, these really should be wiggly signs here because these are just approximate relationships. And then you just keep going. Now we can go from time 2 to time 3 just by using the same method. So I would say that this is an iterative method. just keep repeating. And computers are really good for iterating. And they're really good at breaking things up into really small time chunks and then doing lots of little iterations. And again, the smaller the time chunk, the smaller the value of delta t, the better and better this approximation is going to be. And then the last, and then maybe the most important point, is that this method is easy to adapt to cases where the acceleration is non-constant. And in particular, what makes it such a wonderful method for use in mechanics is in mechanics, as you'll see, we're going to have a method of calculating what the acceleration is. The key equation that we're going to deal with shortly is Newton's second law, which says, this is sort of a spoiler alert, but just so you know where we're headed. We're going to introduce this notion of forces, and if you know the forces that act on the object, you can calculate what the acceleration is going to be. So it's going to be easy to adapt this method to deal with things like, say, a ping pong ball moving through the air, because if we know what the air resistance forces are on the ping pong ball, we can calculate the acceleration, and then each step of the way we can update the acceleration. And even though the acceleration is changing, this iterative method is still going to work really well. So let's see how this works in a real computer program.
I'll show you how to implement Euler's method using the VPython programming language. And what's great about VPython is that as it's doing the Euler's method, it's going to make a little animation of what's going on. So we actually get to see what's happening, what the motion of our object is going to be. It's going to be animated on the screen. And if you haven't done so already, there's an Introduction to VPython tutorial which you should read that's posted on the course website. So we're going to start off with just some boilerplate programming. These are things that you need to have at the beginning of your program. The very first line has to read GlowScript 3.0 VPython. And then the next line, line 2, is a command which sort of sets the scale of the animation that we're going to see. So this command tells us that basically from the center of the screen to the top of the screen is going to correspond to a distance of 50 meters, and that's an appropriate scale because we're going to try to simulate Galileo's ball drop from the top of the tower, not yet leaning, of Pisa. And then before I run this program, which is not going to do very much, I just want to create Galileo's ball here. So there's this command here. It's got a lot of stuff in it. You don't have to worry about all the details here, but the bottom line is that this command is going to create an object called a ball, and it's going to be spherically shaped. It's going to be red, and we've set it up so that as it moves, it's going to leave a little trail behind, sort of like Hansel and Gretel leaving breadcrumbs behind them, which will help us see the motion a little bit more clearly. So if I run this program, what do we see? Well, we see just a red dot in the center of the screen. And by default, the ball was created at the origin of our coordinate system, which we've set up to be right in the center of the screen. Okay, so now let's go back and add a line to the program. So the very first thing I want to do is I want to set the initial condition of where the ball really should be. We want it to be near the top of the screen. So the ball has an attribute called position. So ball.pose is the position of the ball. And we're setting it to these XYZ coordinates. It's going to be an X value of 0. It's going to be horizontally, it's going to be right in the center of the screen. The vertical coordinate, the Y coordinate, is going to be plus 40. So it's going to be near the top of the screen. And then there's actually a z coordinate in this world, but we're going to keep the z coordinate at 0. The z coordinate corresponds to motion in and out of the screen, and we're not going to be concerned with that. So that's the initial position of the ball. And if we run this program, the only thing that's changed is that now the ball is initial position at 40 meters above the center of the screen. Okay, now the next thing we want to do is to set the other initial conditions, and the other initial conditions consist of the initial velocity of the ball and also its acceleration. So in this language, we can name the velocity anything we want, but we're going to call it v, and we're going to set the velocity equal to 0, 0, 0. And you need this VEC here, and the parentheses, that is telling VPython that this is a vector quantity. Velocity is, of course, a vector, and VPython needs to know that. And the acceleration, which is going to remain constant in this story, the acceleration due to gravity, is going to have a value of minus 9.8 in the y direction, and the units are implicitly, everything in this world is going to be in SI units. So the units here are in meters per second squared. And now the other very important part of our setting up the program is to set the time step. And the time step, we can't make a Greek letter delta, so we're going to call the time step dt, and that's going to be in seconds. And for starters, I'm going to make the time step 1/10 of a second. Well, let's see how that's going to work out. So 1/10 of a second. And then I want to set up my Euler's method. So to set up Euler's method, I need, remember, there are two key steps. One is the velocity update, and then the next is the position update. So the velocity update is to set the new velocity equal to the old velocity plus the acceleration times the time step. And notice here, if you haven't done any programming before, this might strike you as odd. The way we assign a new value to a variable is to put it on the left-hand side of the equal sign. And the equal sign doesn't really mean equal here. It means the new value of the velocity is being assigned the old value plus the acceleration times the time step. And the next thing we want to do, so that is, we're going to call that the update velocity. And notice I'm putting anything I write after a number sign here is a comment, and I'm trying to comment everything that we're doing here. So the velocity update is that line, and then the position update, the ball's position, which is ball.position, the new position is equal to the old position plus the velocity times dt. And I'm using, in this version in Python, an asterisk is the way you do multiplication. So this is the position update line. And now we want this to run iteratively, and that requires me to tell you about what's called a while statement. So in VPython, the way you make things run iteratively, there are different programming constructions, but the while statement is the one that we're going to use here. And we want this program to keep repeating as long as the ball is above the ground. So the way we're going to do that is we're going to say, as long as the ball's y-coordinate, and the way we write this is the y-coordinate of the ball is ball.pos.y, as long as that's greater than 0, we want it to run through this while loop, and then we need to put a colon here. And the way, that's the syntax in Python, the while line has to end in a colon, and then the things that are going to be done iteratively have to be indented. So notice I indented these two lines here. And we're almost done. Well, let's run this, and I will show you what happens. I'll show you that it doesn't quite work yet. If we run the program, we didn't really see the ball move. We see it left a trail behind, but we didn't really see it move. And that's because everything happened too quickly. We want this to run sort of in real time. And in order to do that, we need to add this line, the rate command. This tells how quickly it's going to run through these iterative steps. And if you want something to run in real time, the line that you need is rate in parentheses and then 1 over dt. So that means if dt is 1/10 of a second, that means it's going to run through this loop. 1 over dt is 10. So the rate is going to be 10 runs through the loop per second, and that's going to have the effect of making it run in real time. So now let's see what happens when we run the program. The ball is falling, and it's leaving a little bit of a trail behind. But you notice it was kind of jerky, and that's because the time steps were kind of big. So I'm going to make dt 10 times smaller, 1/100th of a second. And now let's run the program. So that's the ball falling, and you really can see it speeding up in a sense, is that there's an equal amount of time between each one of these little drops that it's leaving behind. And you can see that the spacing between successive drops is increasing. That is a sign of acceleration. If we want it to fall a little bit farther, if I want it to fall to the bottom of the screen, I can keep going until y reaches -40. And that is our motion. So that is the way Euler's method is implemented in VPython. And the really great thing is we're going to use Euler's method in VPython, a decent amount in this course, but every single program is going to be just a minor variation on everything that you saw here. So if you haven't done any programming before, don't worry. We're often going to start off with templates that'll get you started, and it'll often just be a matter of making minor tweaks to the templates to get VPython to do your bidding. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye-bye. And one last plug, let me tell you that you should also watch, there's a worked example called Speed Trap, which is the next episode of VPython that will show you a little bit more of the features of VPython. So look for that episode called Speed Trap. See you again soon. Bye-bye.